Welcome to the lesson 15 demo for Math 107 College Algebra. Our answers were all correct on the summary from the previous activity, so we're going to jump to number 1, summary of transformations. All right, given that f of x is our basic or parent function, then g of x, which we will write as a times f of b times x plus c, all plus d, a, b, and c and d are constants. Which of the constants move the function around, shift it, right? So that would be C and D. Those are our shifting. Adding and subtracting causes a shift. Okay, which of the constants change the shape of the function? That would be A and B, right? Multiplication causes a stretch or a shrink, which is going to change the shape. Which of the constants affect the graph horizontally, whether it's by moving it or changing its shape? Horizontal changes always happen within the function, within the parentheses. So that would be B and C. And which of the constants affect the graph vertically, either by moving it or changing its shape? So that would be any constants that fall outside of the function, outside of F. So that would be A and D. And then the effects of the constants that change the graph horizontally versus those that change the graph vertically. So vertically, it's pretty intuitive. It does what you expect, but horizontally is counterintuitive. It's opposite of what you expect. To do transformations, if you have multiple transformations, you first always change the shape of the graph, vertically and horizontally, and then shift it or move it around. Horizontal and vertical transformations are independent, so it doesn't matter whether you do horizontal or vertical transformations first. But you do always have to change the shape and then do your shifting. Now, your book and MyMathLab give you an order for how to do multiple transformations. I want you to completely ignore it. The order presented in this in the videos and the classes will better prepare you for pre-calc and calc. And the two methods are equivalent, but ours requires that the function input be in factored form. So your book will write the input, the stuff in parentheses like bx plus p, and we factor out that first coefficient on the x. So you do, it has b parentheses x plus c. So these two are equivalent. It's just that p is what you get when you distribute the b, so b times c. But we're always going to write it this way and follow these directions. All right, so here's an example of transformation in a real life situation. So we have a function p of t models the growth of a population of fruit flies, and the growth is shown in this graph. A scientist is comparing this to another population, q, that grows the same way, at the same speeds, but starts twice as large. So we're going to sketch a graph of this population on the graph above. So the population of q is always going to be twice that of p. If it starts twice as big and grows exactly the same way, it's always going to be twice as big. So I'm just going to pick some key points and double the y coordinates, double the populations. So here's a point, and then this 3, 3 is going to become 3, 6, and this 6, 2 is going to become 6, 4. I'm just doubling some key points. 7, 0 is still 7, 0 because when you double 0, you still get 0. And then I'm going to connect these, trying to keep sort of the general idea of the graph. This is Q. The one that was graphed originally was P. Okay, so using the language of transformations, I want to compare the graphs of the two functions. The graph of Q is a vertical stretch. Of the function p, and that means that for any input t, the value of the function q is 2 times the value of the function p, or twice. It's 2 times as big. symbolically, I would write Q of t is 2 times P of t.